Hello everyone, I'm Alan. Today, I'm going to present our work, Single-Handed Folding Interactions with a Modified Clamshell Flip Phone. This work is collaborated with Antony and our supervisor Dan in University of Waterloo. So, if you are a similar age with me and had a traditional flip phone around 2000, do you remember the fancy way to use your phone? For example, when answering a phone, just use thumb to pray apart the device with a wrist swing to open the phone and answer a call. Or enjoy a quick flip motion to finish a call with a shake. In my personal experience, flip phones are easy to use single-handed, even with the flipping or folding gestures. However, with current modern flip phones, this type of gesture is harder to perform. Most users would fold their phones with two hands, and the deformable attribute of device is mainly used for mechanical purposes, like minimizing the phone device. So we wonder, what types of single-handed folding interactions are easy and comfortable for users with clamshell flip phones? There are many works explore the bending and folding input method with many different devices. FoldMe studied different folding gestures with a paper-like pad device using two hands. They also combine touch with fold to activate different applications, such as touching a UI widget while folding to change the value. Giro explored one-handed bending gestures with a deformable phone prototype. 4 bending locations were preferred, such as bending on the corners or in the middle of phone vertically. Kirschenbaum and Robson studied and defined the bending events with a simplified 1 degree of freedom bendable device. The bending prototype is similar to current flip phones. These works either study 2 hand gestures with specialized bending prototype or mainly focusing on detection. We specifically explore the folding interaction single-handed with a prototype based on current modern flip phones and evaluated the gesture preference and performance. To explore the folding interactions, we first define the input space. We define a flip phone with 2 sections, top and the bottom, and 2 surfaces, front and the back. Then, we assume there is a double-acting hinge to enable 2 folding directions, folding inward or folding outward. The sensor inside the device can also sense the continuous folding angle as a folding magnitude. Then, as a smartphone, the device will support touch input in the front, and also the back of the device touches in the top section of the back. With the limitation of hardware prototype, we explore the input space with 8 touches. Then we propose 3 types of folding interactions. Only fold describes gesture that folding the device without touch. Like the video shows, we can have a small outward fold or a medium inward fold. Touch enhanced fold is the gesture that touch the screen first and then fold the device, such as touch the location 22 and perform an outward fold shown in the video. Last, fold enhanced touch is the gesture that fold the phone first, then touch the screen, such as folding the screen inward and touch the location 2-3. To explore and study these 3 folding interactions, we built an evaluated prototype with a shape similar to a modern flip phones. There are still some differences between our prototype and the modern flip phone. First, to support 2 folding directions, we use a double-acting hinge, shown in the right image. And to enable discrete folding gestures and reduce the effort to unfold the device, a spring was added in the middle of the prototype connecting 2 sections. The spring would provide the force to unfold the device. And we also support back-of-device touches by simply turning the prototype around. Before we dive into our experiment and results, here are some simulated applications showing what folding interaction can be used with our modified clamshell flip phones. For text editor, we can touch a word and fold inward to cut a word off the paragraph, and touch a place to fold outward to pass it back. We can also use fold enhanced touches to activate system shortcut, such as apply color. For map application, we can simply folding outward or inward to zoom in or out. Touch a location first and fold can zoom specifically to that location. And we can also differentiate a light tap or a hard tap with a folding angle, such as a light tap to open a day schedule and a hard tap to directly aid in an event. Folding enhanced touch can also be used to improve reachability. We can fold the device to bring down the UI and perform the touch easily to reach target items. We conducted an experiment to investigate gesture speed, gesture arrows, how participants change their grip to perform such gestures, and their preference. We measured time, arrow count, and 4 subjective ratings, including ease, comfort, confidence, and acceptance. Overall, we found folding gesture can be performed quickly. And here shows the result of all 30 gestures we investigated. We labeled those gestures with slower speed, higher arrow count, or lower ratings in red. So as the result shown here, still more than half of folding gestures are rated easy and comfortable to perform. One interesting result is how participants perform these folding gestures. And by observing the participant, we found usually there are multiple ways to fold the device for the same gesture. Take the folding outward, for example. Some participants would use their thumb and index finger to fold the device while their middle finger is in the hinge area on the back as a support. But some participants would totally change their grip and hold the device from the front surface and folding outward with index finger. We also found when combining fold and touch, better finger dexterity and coordinations were required, especially for fold enhanced touch. We observed some participants would fold the device while using their thumb pressing down the surface near the hinge area, and then slide to the target location to perform such gesture, due to it's difficult to touch the location while maintaining the folding angle. So we summarize some design recommendation. First, only fold gesture could be used for frequent functions since they are easy to perform. For folding direction, inward fold is preferred because our natural finger blade placement is in the back of the device. Small fold is fast, but it could be harder to control. Some participants would exceed the angle threshold and become a medium fold. And we found reachable areas with the thumb is even smaller when combining with the touch. So when we need to use our fingers and palm to fold the device, our thumb would be harder to move around and reach the locations. Finally, we want to describe the future clamshell flip phone we imagine and based on our results. So current foldable screens use the rail systems. We can fold the device inward, but it's possible to extend the system to enable an outward fold too, especially participants prefer a small outward fold. And our results show folding gesture can be performed quickly. So to cooperate a spring system, a time-based locking mechanisms is possible to use. For example, when folding a device and let go within 2 seconds, the device will return back to the flat status. But when folding the device and hold it longer, the device will lock the angle similar to the current flip phones. And last, current flip phones already have a touch screen on the top section of the back. We can integrate the touch events of these 2 screens and enable back-of-device touches. In conclusion, we demonstrate a new example of how deformation gestures can be used as an input method. And by supporting this folding interaction in the modern flip phones, we may be able to use the phone the same way as we use our traditional flip phones, with those simple, fancy, and zazzy gestures.